Good evening, everyone. Welcome to this weekly Scrum meeting. I'd like to update you on the progress of my deep learning model for heart disease prediction. So I used PyTorch. I built and trained a neural network with two hidden layers and dropout to prevent overfitting. And after training, the model achieved an accuracy of 84% on test set with a balanced precision and recall across both classes. This indicates reliable performance in identifying both healthy individuals and those with heart disease. I faced some compatibility issues with the typing extension module where I encountered, which were resolved by updating the necessary packages and ensuring our environment is correctly configured. So for the next and following week, I plan to experiment with different learning rates, batch sizes, and the network architecture to further enhance the model's accuracy and robustness. And I also want to handle the class imbalance. Although our current results are promising, I aim to address any potential class imbalance more thoroughly by integrating techniques like smooth or adjusting class weights during training. And once optimized, next phase will involve deploying our model into our application pipeline, enabling real-time heart disease prediction and integrating it to our seamless at-home care support. I will hand it to uh, next
Me.
member. Yeah,
Thank you.
please
Thank you,
go ahead.
Chenxi. Yeah. So this week I focused on implementing cross-validation with early stopping for my logistic regression inspired neural network model. Similar to my work on the KNN inspired model, I used a five-fold cross-validation approach to ensure the model's robustness and generalization across different data splits. During training, early stopping monitored the validation loss and halted training if no improvement was observed for a set number of epochs, preventing overfitting and maintaining the best performing model state for each fold. The results demonstrated consistent and balanced performance across classes. For instance, the average accuracy across all folds was 85%, with precision scores of 86% for class 0 and 84% for class 1. The F1 scores were 87% for class 0 and 84% for class 1, reflecting a reliable balance between precision and recall. I also visualized training and validation loss curves for each fold, which showed smooth convergence and further confirmed the effectiveness of early stopping in preventing overfitting. And next week, I plan to compare and summarize the findings from both my KNN-inspired and logistic regression-inspired models, as well as other models developed by our team. I will also begin preparing the final report, consolidating our group's work and results into a cohesive document that highlights key insights and achievements. And that's all for my part. And I'll pass it over Xiaoyu.
Thank you, Qianying. So this week I focus on applying decision tree and logical regression concepts to enhance our deep learning implementation. Inspired by those models, I worked on integrating interruptibility and feature importance analysis into the neural network. Specifically, I employed techniques that mimic how decision tree splits data and how logical regression handles learner relationships. Those effects aim to improve the explainability of our deep learning models while maintaining its predictive accuracy. Currently, I'm analyzing the results to compare the performance and insight from both traditional models and the deep learning approach. This comparison will help us identify the strengths of each method and guide our recommendation for real-world application. So for the next week, I plan to consolidate and summarize our group feeding comparing the traditional and the deep learning models in detail. Additionally, I will begin preparing the final report focused on interpreting our results and presenting insights. This work will ensure that our project outcome are well documented. So that's all for my part. Now I will pass to Xiaoyi. Thank you.
Thanks, Xiaoyu. This week, I did a series of parameter adjustments to explore potential enhancements in model performance. The aim is to strike an optimal balance between training efficiency and model accuracy. First, the architecture of our neural network in the heart disease model class consists of several layers with the ReLU activation and the dropout for regularization. I found the optimal dropout rate of 0.3 after experimenting with a range of values starting from 0.2 to 0.5. Dropout prevents overfitting by randomly setting a fraction of input units into 0 during training, which helps in creating a more generalized model. Secondly, the learning rate in the optimizer setting is critical for convergence. The best learning rate, 0.0001, was concluded by testing learning rates between 0.001 and 0.00001 to observe their impacts. A higher learning rate can lead to faster convergence, but might overshoot minimum, while lower learning rate ensures more stable convergence, but at the risk of getting stuck in local minima. Additionally, adjust the batch size in the data loader for both training and testing data sets. Finally, I set it at 16, the most suitable value, but I've explored sizes from 16 all the way until 64. A larger batch size provides a more accurate estimate of the gradient, but requires more memory and may lead to a smoother training process, potentially impacting the model's ability to generalize. For model training, I introduced an early stopping mechanism with a patient's parameter optimally set at 20 epochs. Adjusting this parameter from 10 to 30 helps in preventing overfitting by stopping training if the validation loss does not improve for a specified number of epochs. For next week and the rest of this week, I'm going to prepare for the final presentation and report by wrapping everything up. That's all for my part. Next is Jalen.
Okay. Wait a minute. I use my mobile phone. Sorry. Last week, I still pay more attention on the deep learning model part to predict heart disease. First part, I try to modify or optimize the pre-processing the data part, handling some missing values like inputting them with medium instead of dropping them to increase the prediction accurate rate. And then I standardized the features and used RFE, which is recursive feature elimination, to select the most important ones. Instead, what I have done with the DNN, I try to add some CNN, like with the multiple layers, incorporate dropout and batch normalization to prevent overfitting. And I tightened hyperparameters like the number of neurons, learning rates, and dropout rates used by sign optimization. With all these efforts, my models this week, the text accurate is above the 90%. Maybe I guess I remember it's 91 now. And I also experimented with ensemble method like voting and stacking classifier, combining the neural network with algorithm like random forest and KNN, but don't see I think still have some distance to the 92%, which is the result of the original paper. So I plan to moving forward to higher accuracy with other efforts for next week. That's all for my part.
Thank you, Jalen.
Thank you, Jalen.
Thank you, everyone.
You.
Thank you. Good night.